Here you are, sitting there, perhaps on a comfy couch, or maybe hunched over a desk, a screen glowing softly in front of you. Take a moment, just a tiny one, and consider the sheer improbability of your existence. Not just you, the individual, but the chair you're in, the building around you, the planet beneath your feet, and the sun that warms it. All of it, every single atom, a cosmic legacy. Born from processes so grand, so ancient, they defy easy comprehension. Today, we're not just going to talk about those processes. We're going to journey through them. Forget the typical voiceover, the dramatic music, the sweeping visuals. We're going to delve, step by deliberate step, into the scientific narrative of how galaxies, the colossal cosmic islands that house billions upon billions of stars, and entire civilizations come into being. This isn't a speculative flight of fancy. It's a meticulously constructed story, pieced together by generations of brilliant minds, painstakingly observing and analyzing the faint whispers of the universe. So, buckle up, or rather, just settle in, because the story of galactic birth is far more profound and far more fascinating than any fiction. It's a tale of gravity, of quantum fluctuations, of the invisible scaffolding that shapes the cosmos, and of the slow, relentless dance of matter. Our story begins not with a bang, but with something far more subtle, far more fundamental, the very fabric of space-time itself. Imagine, if you can, a time, an epoch, really, when the universe was incredibly young. We're talking fractions of a second after the Big Bang, a period known as the Planck epoch. During this unimaginably brief instant, all for fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified. The universe was a superheated, superdense soup, a quantum foam where the very notions of space and time as we understand them began to solidify. As the universe expanded and cooled ever so slightly, these forces began to Gravity was the first to emerge as a distinct force. This is crucial because gravity, as we know, is the architect of structure in the universe. But at this earliest stage, there wasn't much structure to speak of. The universe was incredibly smooth, almost perfectly uniform, almost. Here's where it gets really interesting and a little bit mind-bending. The universe, at its very inception, wasn't absolutely, perfectly uniform. Quantum mechanics, that wonderfully weird branch of physics that governs the behavior of matter at the smallest scales, tells us that there are always tiny, inescapable fluctuations in energy, even in a vacuum. These are known as quantum fluctuations. In the incredibly hot and dense early universe, these tiny fluctuations in energy translated into incredibly tiny, but crucially important, fluctuations in density. Imagine a perfectly smooth, perfectly even surface, but with microscopic ripples, some areas infinitesimally denser than others, some infinitesimally less dense. These aren't the kind of ripples you'd see with your eyes, not even with the most powerful microscope. These are at the quantum level. But here's the kicker. The universe underwent an astonishing period of rapid, exponential expansion, known as inflation. During inflation, the universe expanded by a mind-boggling factor, something like 1026 times in a mere fraction of a second. This incredibly rapid expansion had a profound effect on those tiny quantum fluctuations. It stretched them out, magnifying them from subatomic scales to macroscopic scales. Those infinitesimally small density variations were blown up to sizes that would eventually become the seeds of galaxies and even galaxy clusters. Think of it like this: if you blow up a balloon with a tiny, imperceptible smudge on its surface, that smudge becomes much larger and more noticeable as the balloon inflates. Similarly, inflation took those quantum smudges in the early universe and stretched them across vast cosmic distances. So when inflation ended, approximately 10 to 32 seconds after the Big Bang, the universe was still incredibly hot and dense. But now it possessed a crucial ingredient, a primordial tapestry of slightly overdense and underdense regions. These density variations were incredibly subtle, perhaps 1 part in 100,000, but they were the embryonic blueprints for everything we see today now. Let's fast forward a bit through the quark epoch and the lepton epoch. As the universe continued to cool and elementary particles began to form, we arrive at what's known as the photon epoch, where the universe was still too hot for atoms to form. It was a plasma, a soup of free electrons and atomic nuclei, mostly hydrogen and helium. Photons, particles of light, were constantly scattering off these free electrons, making the universe opaque. Light couldn't travel freely. It was constantly being deflected, like a ball bouncing around in a pinball machine. This period lasted for about 380,000 years. During this time, gravity, ever so slowly, began its tireless work. Those slightly overdensed regions, the magnified quantum fluctuations, began to exert a tiny bit more gravitational pull than their less dense surroundings. This meant that matter, ever so subtly, began to trickle into these slightly denser pockets. It was a slow, almost imperceptible process at first, like water very gradually collecting in the shallow depressions of a vast, flat landscape. Then came the moment of cosmic liberation. As the universe continued to expand and cool, the temperature eventually dropped to around 3000 Kelvin, about 2700 degrees Celsius. At this temperature, electrons were finally able to combine with atomic nuclei to form neutral atoms, primarily hydrogen and helium. This event is known as recombination. The formation of neutral atoms was a pivotal moment. Why? Because now, with electrons bound within atoms, photons were no longer constantly scattering off free electrons. The universe suddenly became transparent. Light, for the first time, was free to travel unimpeded across the cosmos. This ancient light, redshifted by the expansion of the universe, is what we observe today as the cosmic microwave background, CMB radiation. The CMB is literally the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. And guess what? When scientists precisely measure the CMB, they don't find a perfectly uniform glow. They find those tiny temperature variations, those echoes of the primordial density fluctuations that were stretched out by inflation. These are the direct observational proof of the seeds of cosmic structure. It's like looking at a baby photo of the universe and seeing the subtle features that would eventually grow into the magnificent structures we observe today. Now, with the universe transparent and the CMB providing our initial conditions, the stage was set for the next grand act, the Dark Ages. This period, lasting from about 380,000 years to several hundred million years after the Big Bang, is not dark because there was no light. There was the CMB, but there were no stars, no galaxies, no luminous objects as we know them. It was a period of cosmic quiet, a time when gravity was diligently, relentlessly doing its work in the darkness. During the Dark Ages, those slightly overdense regions, those cosmic puddles of matter, continued to pull in more and more material due to their slightly stronger gravitational attraction. This process was slow, agonizingly slow by human timescales, but over hundreds of millions of years, it was profoundly effective. The tiny density enhancements grew, like invisible ripples in a pond gradually accumulating water. Here's where dark matter enters the picture. You've probably heard of dark matter. It's a mysterious substance that doesn't interact with light, hence dark, or other electromagnetic forces, but it does interact gravitationally. And here's the crucial part. Scientists believe that dark matter made up about 85% of the total matter in the universe during the Dark Ages. Normal matter, the stuff we're made of, was only about 15%. This is a huge deal. Why? Because normal matter, being subject to electromagnetic forces, experiences pressure from photons. In the early universe, this pressure would have resisted the gravitational collapse of those density fluctuations. But dark matter, being impervious to light, felt no such pressure. It could collapse unimpeded. So, the dark matter effectively formed the gravitational scaffolding for the large-scale structure of the universe. Imagine an invisible, intricate web of dark matter filaments and halos, slowly coalescing and growing denser. These dark matter halos were the first significant structures to form in the universe, long before the first stars flickered into existence. They were the gravitational wells, the cosmic cradles, where the first galaxies would eventually be born. As these dark matter halos grew, they began to pull in the normal matter, the hydrogen and helium gas that was diffused throughout the cosmos. This gas, like water flowing downhill, began to accumulate in the gravitational potential wells of the dark matter halos. It was a gradual infall, drawing in more and more material over vast stretches of time. As the gas fell into these nascent dark matter halos, it gained kinetic energy, heating up. But it also had a way to cool down. Hydrogen and helium atoms, when they collide, can emit photons, releasing energy and allowing the gas to cool. This cooling was essential because for stars to form, the gas needs to be able to collapse further, and collapse is resisted by pressure heat. So, within these accumulating gas clouds, embedded within their dark matter halos, the conditions were slowly becoming ripe for star formation. The gas would continue to cool and become denser, eventually reaching a point where gravitational collapse could overcome the internal pressure. This is where the magic really begins. The densest pockets within these gas clouds would collapse, further fragmenting into smaller and smaller clumps. As these clumps continued to collapse, their cores would heat up due to the increasing pressure and density. Eventually, in the very densest and hottest cores, the temperature and pressure would become so immense that nuclear fusion would ignite, and with that, the first stars were born. These first stars, often referred to as population 3 stars, were likely very different from the stars we see today. They would have been massive, hot, and short-lived. Why massive? Because the early universe had virtually no heavy elements, no carbon, oxygen, iron, or anything heavier than lithium. These metals, as astronomers call them, are crucial for cooling gas efficiently at lower densities, allowing smaller stars to form. Without them, it was harder for the gas to shed enough energy to fragment into smaller pieces, thus leading to the formation of much larger stars. These behemoth population 3 stars, perhaps hundreds of times the mass of our Sun, would have burned through their nuclear fuel at an incredible rate, living for only a few million years before exploding as supernovas. These supernovas were not just spectacular cosmic fireworks. They were absolutely vital for the next stage of galactic evolution. When these massive stars exploded, they didn't just release enormous amounts of energy. They also forged and dispersed the first heavy elements into the surrounding gas. Inside the cores of these first stars, through nuclear fusion, hydrogen and helium were transmuted into carbon, oxygen, nitrogen, and other elements, up to iron. And in the spectacular violence of the supernova explosion itself, even heavier elements, like gold and uranium, were created. This enrichment of the cosmic gas with heavier elements was a game changer. These metals acted like cosmic coolants. Even tiny traces of these elements made it far more efficient for subsequent generations of gas to cool and collapse. This meant that the next generation of stars could be smaller, more numerous, and live much longer, like our own Sun. As more and more stars formed within these early dark matter halos, they began to illuminate the universe, ending the Dark Ages. This period is known as the epoch of reionization, as the ultraviolet light from these first stars reionized the neutral hydrogen gas throughout the universe, transforming it back into a plasma. This process, driven by the collective luminosity of countless nascent stars, made the universe transparent to even more wavelengths of light. Now, we're not just talking about individual stars anymore. We're talking about the emergence of the first galaxies. These early galaxies were likely much smaller and clumpier than the grand spiral and elliptical galaxies we see today. They were irregular, chaotic collections of gas, dust, and millions of stars, still embedded within their overarching dark matter halos. And here's where the story gets even more dynamic. Galactic growth wasn't a static process. It was, and still is, a story of mergers and acquisitions as the universe continued to expand. The gravitational pull of those large-scale dark matter filaments and knots became even more pronounced. These filaments acted like cosmic highways, drawing in not just individual gas clouds and stars, but entire nascent galaxies. Imagine countless smaller galaxies, each a gravitational island of stars and gas, slowly being pulled towards each other. When two galaxies get close enough, their mutual gravity begins to distort and stretch them. Stars are ripped from their orbits, gas clouds collide, and a spectacular cosmic dance ensues. This is a galactic merger. Galactic mergers are messy, violent, and incredibly important for galactic evolution. They trigger bursts of star formation as gas clouds are compressed and shocked during the collision. They can reshape galaxies, transforming spiral galaxies into elliptical ones, or fueling the growth of supermassive black holes at their centers. Over billions of years, these smaller, irregular protogalaxies repeatedly merged and accreted more gas and stars, growing larger and more complex. Our own Milky Way galaxy, a majestic spiral, is believed to have formed through a long history of such mergers, swallowing smaller satellite galaxies and accreting vast amounts of gas over cosmic time. In fact, we are still merging with the Sagittarius, dwarf's spheroidal galaxy right now. The morphology of galaxies, why some are spirals, some are ellipticals, and some are irregular, is also intricately linked to their birth and evolutionary history. Spiral galaxies, like the Milky Way, are characterized by a rotating disk of stars, gas, and dust, with prominent spiral arms. These galaxies typically have ongoing star formation. As gas continues to cool and collapse within the disk, they tend to form in regions where the gas has been able to settle into a rotating disk without too many disruptive mergers in their recent past. Elliptical galaxies, on the other hand, are typically older, more spherical or egg-shaped, and contain very little gas and dust. Star formation in elliptical galaxies has largely ceased. They are often thought to be the end product of major galactic mergers, where the violent collision disrupts any existing disk structure and funnels gas towards the center, leading to a burst of star formation that quickly uses up the available gas. Irregular galaxies, as their name suggests, have no defined shape. They are often the result of ongoing interactions or mergers, or they might be relatively small galaxies that haven't yet settled into a stable configuration. At the heart of almost every large galaxy, we find another fascinating and powerful entity, a supermassive black hole. These cosmic behemoths, millions or even billions of times the mass of our Sun, are intimately linked to the formation and evolution of their host galaxies. While the precise mechanism of their formation is still an active area of research, it's believed that they grew in tandem with their galaxies, feeding on gas and stars that spiraled into their gravitational maw. The energy released as matter falls into these black holes can also dramatically influence their host galaxies, sometimes even halting star formation by heating and expelling gas. This feedback mechanism is a crucial part of the complex dance between a supermassive black hole and its galaxy. So, the story of galactic birth is not a singular event. It's an ongoing cosmic drama, stretching across billions of years. It began with the faintest quantum whispers in the primordial universe, amplified by inflation, guided by the unseen hand of dark matter, ignited by the first generations of massive stars, and sculpted by a relentless ballet of gravitational attraction and spectacular mergers. From those initial tiny fluctuations. Through the Dark Ages, the epoch of reionization, and the countless mergers and star-forming frenzies, the universe has painstakingly built the grand cosmic structures we observe today. Every star, every planet, every living thing is a testament to this incredible journey. The atoms that make up your hand, your eyes, the very air you breathe, were forged in the hearts of long-dead stars scattered across the cosmos by supernova explosions, and eventually gathered together by gravity within a swirling galaxy. And this process is not over. Even now, as you sit there, galaxies are continuing to evolve, merging, forming new stars, and perhaps even giving birth to new planetary systems. The universe is a dynamic, ever-changing canvas, constantly being repainted by the fundamental forces of nature. So, the next time you gaze up at the night sky, or even just ponder your place in the universe, remember this story. Remember the infinitesimally small beginnings, the unseen scaffolding of dark matter, the cataclysmic births of the first stars, and the endless dance of galactic mergers. It's a story written in the stars themselves, a testament to the elegant, powerful, and utterly astounding processes that have shaped the cosmos and ultimately brought you into existence. It's a universe that is both ancient and eternally new, a place of wonder and discovery, still unfolding its secrets before our very eyes. And you, dear viewer, are a tiny yet integral part of this magnificent ongoing saga. Now go forth and marvel.